Okay, welcome back everyone. In this video we're going to review the ideal gas law. Now chances are you've probably already learned about this in chemistry, but if not, we'll go through a short derivation. So one thing you should have noticed in our lab in physics is that if you take pressure and volume and multiply them, you get a constant. So this is what we will call Boyle's law. And again, you might have heard about this before. And what this says is that any combination of pressure and volume will be equal when you multiply them together, because they're equal to a constant and they happen to be equal to the same constant. Now in chemistry, you should have also have seen that if you take the ratio of volume to temperature, that is also a constant. And that is what we call Charles' law. So with this, we can say V1 over T1 equals V2 over T2, again because they're equal to the same constant. So if we put these two laws together, then what we get is that PV over T is equal to some new constant, which is a combination of the two constants from Boyle's law and Charles' law. So if this is constant number 1 and constant number 2, this is going to be constant number 3. And it doesn't matter if you multiply them together, it's still just a constant. And so then we can write this as P1V1 over T1 is equal to P2V2 over T2. And this is actually a very useful equation to use if we're talking about a situation where there's an ideal gas and we have a constant amount of gas. So in other words, no gas is entering or leaving the system. So that's pretty useful. But it becomes even more useful if we extend it to situations where the amount of gas changes. Now in order to do this, we need to write a slightly different equation. We need to add in the number of molecules. So I can write it like this: PV over NT equals constant. And so N is the number of molecules. We can kind of relate this to a constant that we know about, and it turns out that this constant right here, Kb, is called the Boltzmann Constant, and it has the value of 1.38 times 10 to the negative 23rd joules per Kelvin. So the units of that look a little bit weird, but they do work out. Now, if we want to make this an even more general statement, and not just about the number of molecules, but if we want to talk about the number of moles, then we want to use what you might be more familiar with when we say the ideal gas law. And that is simply PV-NRT, PV equals nRT. And one thing that I want to point out is that there's a very simple relationship between R and Kb, the Boltzmann constant. And notice that in this equation I'm using a capital N for the number of molecules, but here I've got a lowercase n, which is the number of moles. Well, how are those related? Well, we know that the number of moles is going to be the number of molecules divided by Avogadro's number. So this is a neat little way to link these together. And of course, Avogadro's constant is 6.022 times 10 to the 23rd. That's the number of molecules per mole. Now one thing I do want you to keep in mind when we're using the ideal gas law is that it applies to real gases. It does work in real life, but these real gases have to have fairly low densities and fairly low pressures. when you start talking about a compressed gas, it doesn't really obey the ideal gas law. Molecules are very close together. There's a lot of intermolecular forces, one molecule pulling on another, and as a result, we can't make many of the assumptions that allow us to write the ideal gas law in the first place. And that's going to actually be a separate video. I'm going to derive the ideal gas law so that you can see how the things that you've been studying all year, momentum, energy, temperature, all come together to form this ideal gas law. So that's it for now. Take a look at the next video, which is how to deal with the units in the ideal gas law.